Welcome, and thanks for joining this lecture on NPUs driving smarter vehicles and robots. In this talk, we'll follow the perception, decision-making, and action pipeline and see how on-device neural processing enables low-latency control, safer reactions, and reliable autonomy without constant cloud dependency, setting the stage for the technical details ahead. In this slide, we summarize key NPU performance benchmarks for real-time edge processing. Efficiency measured in TOPS per watt, deterministic latency targets under 10 milliseconds, single inference batch 1 throughput, on-chip memory bandwidth for fast data movement, compliance to functional safety standards like ISO 26262, and the all-important cost per unit that determines commercial viability. This slide highlights HydroNet, a multi-head network that runs object, lane sign detectors in parallel on NPUs. Benchmarks show about a 2.8 times execution speedup versus CPU, GPU, an end-to-end latency around 87 milliseconds, and greater than 54% PE utilization, which translates directly to earlier braking and smoother path planning in autonomous systems. Here, we look at an automotive SIP architecture and its scalability model, a monolithic array of 9,216 processing elements is partitioned into modular 4x2 chiplets using network-on-package interconnects, enabling an 82% throughput gain for a roughly 10% energy trade-off and allowing right-size compute configurations across L2 to L4 autonomy levels for different vehicle classes. The market chart traces automotive NPU growth from roughly $2.2 billion in 2024 to about $17.1 billion by 2034, implying a near 21% CAGR. Key demand drivers include deeper ADAS penetration, EV powertrain analytics, software-defined vehicle platforms, and edge-based safety mandates that push intelligence into the vehicle rather than the cloud. This slide shows integrated EIQ Neutron NPUs inside Cortex-M33 MCUs, enabling local AI inference. By fusing camera, IMU, and proximity data on each chip, NPUs generate sub-100 millisecond motor commands, removing cloud dependency for critical control and meeting stringent performance targets while supporting convolutional, recurrent, and transformer models for diverse sensing tasks. The comparison between NPU and GPU emphasizes power and mechanical impact. GPU inference averages around 15 watts, whereas optimized NPU inference can be as low as about 2 watts, extending runtime and reducing cooling needs. That efficiency shrinks robot weight and complexity and enables applications like drone swarms with longer flight times, higher payloads, and enhanced swarm coordination. Empirical results show that NPU-accelerated stacks reduce multi-object tracking latency by roughly 40% and cut false positives by about 18% compared to CPU-ONE systems. Those measurement gains map directly to real-world benefits, such as shorter stopping distances and a materially lower collision probability in automated driving and robotic navigation. This slide contrasts on-device NPU, cloud offloading, and a hybrid fallback approach. On-device NPUs offer guaranteed determinism and sub-20 millisecond reactions independent of connectivity. Cloud offloading introduces unpredictable 100 millisecond plus delays, and a hybrid model combines deterministic safety control with cloud scale for fleet learning and non-critical updates. Automotive-grade NPUs face cost and validation hurdles. Advanced 16 nanometers FinFET masks and AEC-Aq 100 qualification plus ASIL diagnostics drive up component expense and lengthen validation cycles, pushing per-unit costs above tight thresholds and constraining adoption among economy vehicles and small batch robot makers, despite the clear technical benefits. This slide addresses security threats to local NPU inference, where physical access to weights or sensor data can enable model theft, adversarial inputs, and spoofed braking or steering. Mandatory countermeasures include secure boot, encrypted DRAM, and side-channel resistant microarchitecture, which together help prevent model extraction and block malicious inputs at the hardware level. Finally, NPU architecture is evolving toward 3 nanometers, GAA process integration, with sparsity acceleration, on-chip MRAM, and safety islands, to target around 50 TOPS per watt by 2027, while open standards like RISC-V vector extensions and unified SDKs aim to democratize NPUs, enabling Tier 2 suppliers and service robot deployments across broader markets.